Good evening and welcome to this Academy lecture. It's a pleasure for us to see you all here. And it's a particular privilege to welcome Professor Stanislav Smirnov from the Universite de Geneve, who will give tonight's lecture. He will be introduced by the chair of our class for mathematics, Professor Nils Dencker. So most welcome.
So, today's speaker really shouldn't need any introduction because he's worked 7 years at KTH in Stockholm, but those of you who missed him, I give you a short resume that Stanislav Smirnov was born in St. Petersburg. He won the Mathematical Olympiad twice, and he graduated from St. Petersburg and took his PhD from Caltech. And he's been working in Yale, the Institute of Advanced Study, and at the Max Planck Institute in Bonn. And he worked at KTH in 1998 to 2005. Presently, he's both at Geneva University, School Tech in Moscow, the Chebyshev Lab in St. Petersburg, and he's also here. And he's been having several prizes and awards. He got the Clay Research Award 2001, the Salem Prize in 2001-2, a great year. He got the EMS Prize in 2004, and above all others, the Field Medals in 2010. And he's going to talk about what is a random walk. Please.
Yeah, so thanks very much. It's a great pleasure to be back and a great honor to speak here. And I will try to speak about one of the subjects which is very nice in the way that it showcases the good connections of mathematics with other areas. And this is a subject about random walks and different variants thereof. So the first sort of question about this arose from biology, and it is intervened with the names of two famous scientists who actually are more famous for other things. So that's Jan Ingen, who discovered the photosynthesis, but also he was basically the first person to run a scaled vaccination program. So he talked Empress Maria Theresa to undergo vaccination, and then many of her subjects did. And Robert Brown, who discovered the cell nucleus, and he lived a bit later, and that's why he's unhappy, because it's not a painting, it's a daguerreotype, and so he had to sit 5 minutes with this pose. And now there is a painting of him, and this is his microscope with which he discovered the cell nucleus. And the interesting thing was people won't debate whether he actually saw it or not, because the microscope is rather primitive. There is no tubes, there are only 3 lenses, and they, I think, discovered it fairly recently in Scotland in the archives, and the people actually tried, and I think that this picture is actually made through this thing. So it's actually, you can see the nucleus of a cell. So one thing he observed was, and you hear about in the biology class at school, is what is called now Brownian motion, and it's a sort of erratic motion of small particles under the microscope. So for some crazy reason, half of the biology textbooks in school say that the grains of pollen move erratically. So probably one can trace it to the first book which had this misprint. So actually, they are too big to undergo Brownian motion. So it's what he observed, some small particles inside the grains of pollen, which are usually hollow inside and have what is called in biology vacuoles. And he got very excited because he thought that he saw the kind of a source of the living matter, what makes the matter alive. So he observed it for 3 months, published an article, and I like very much, it's like 19th century articles were called like 19th century novels, so it's a brief account of microscopical observation taken the months of June, July, and so it's very, very, very detailed. And then he lists all his regalia, and here he says that he's a member of the Royal Academy of Sciences of Sweden, so that's the first one after all the British abbreviations. And I think then there is Denmark, and then there is St. Petersburg. So it's then it's very it actually reads very nicely like a novel, because what I like very much about old papers, what people don't do anymore. He writes also about unsuccessful things. He writes that I thought this, it didn't work, I thought that, it didn't work. So first he got very excited and he thought that it's a source of life in the matter. There is like these small batteries or whatever, small molecules which make plants alive. And then he tried to look at the old dead plants. Still there was movement. He took the herbarium, then he took rocks, and then he said, well, I decided to take old rocks of all ages, so I took a part of the Sphinx, which he found in the... So he chopped this piece off. Well, Napoleon's soldiers chopped this piece off, but so he took one of it, and he always saw this movement, and the conclusion was that it's not biological in nature, but it's physical in nature. But being a good scientist, he still continued his studies. So first he published an article, but he continued his studies. Really, it's very interesting read. So he tried it in a dark room. He tried it horizontally, vertically, tried to outlaw all vibration. So basically the conclusion was that there is a physical reason for this movement, but I don't know which one. And we exclude A, B, C, D, and so on. The atomic theory, then it was, well, I mean, even Greeks already had the idea that matter is not continuous, but rather split into small atoms, and hence they got atoms from Leucippus and Democritus. But at that time, it was not widely accepted. Basically, 1/3 of physicists thought that it's out of atoms, 2/3 that it's continuous. But some people immediately suggested the idea that what he sees like a particle which is blue, which is big, and it's moved by molecules bumping into it. But molecules are too small to see in the microscope. So what actually happens is that this is what happens, and this is what we actually see. We just see the movement of blue particle because those are too small. And immediately one can argue, for example, that if you change the temperature, if particles start moving faster, so I'll do this trick to move them faster, then your particle, if molecules move faster, so your particle also will move faster. So then you immediately can argue that there should be you should be able to observe that this is caused by molecules, because then the bigger is the temperature, the faster will be the movement, because the molecules bump faster. But people discussed it qualitatively, didn't do any experiments, and then the interesting thing is that the next advance came from the direction of mathematics, and it was done by Albert Einstein. So the thing mathematician tries to do in such a circumstance is to make a mathematical model which would be simplified but still retain the main properties of the physical phenomenon. So the model is that you have, it's called a random walk, so you take a particle, you just jump at random times in random directions. So it's say 6 sigma meters on average n times per second. We can simplify it. It turns out that further simplification doesn't ruin the model. So we fix sigma, that all the jumps are of the same length, and we restrict it to 4 directions. Like here we jump east, north, east, east, south, west, north, north, east. Actually, here you already notice that the trajectory in the plane, it can go over the same place, so it's easy to watch it with time, how the particle moves. But if you decide to plot a graph, you'll get some sort of complicated thing. If you study it on the plane, it's actually sufficient to look at one coordinate, how it moves left or right, or how it moves up and down, and treat them separately. And the same, the same, let me show the next picture, same you can do in 3 dimensions. Again, it's sufficient to take one of 3 coordinates, and in fact, the Brownian motion is actually in 3D. We just, in the microscope, we see only 2 dimensions. And in 2 dimensions, it's also in mathematics, it's often said that it's a problem about the drunken sailor. And the idea that you are in a city which is more like Manhattan, than Stockholm, that it's perfect grid of streets, and the sailor comes out of a bar completely drunk, and he walks to the intersection, he drops dead, then he gets up, he doesn't remember where to go, he goes in the random direction, and then he undergoes random motion, and then you can ask question, for example, how soon he will get to the port. Or what's the bigger probability to get to the port or to return to the bar where he started? Or how far he gets after 1,000 dropping down and getting up. And this is more or less the same question. So here we fix the grid, we fix how often he goes. And if we keep just one coordinate, so this is the easier to plot because we can plot the time horizontally, and then this is a coordinate. So basically it's a easiest probability model. It's what probabilists understood how to do even 200 years ago, very well in 300. So we toss a coin, And if it comes up tails, you go up. If it comes up heads, you go down. And then here are how the trajectories look. Of course, there is a chance that 100 times in a row you toss head. And then it will go down, down, down like that. But 100 times in a row, it's like 10 times in a row, probability is 1 in 1,000. 100 times in a row, probability is 1 in 10 to the power 30, which is, well, not as much as the number of particles in the universe, but still very well in this direction. So it's highly unlikely. So most trajectories, they look like that, and you see actually that after 100 steps, you get away not so far, like 17 minus 19, so it's usually much less. And mathematical problem would be how far we get away. Well, one way to formulate it is that x is our position. So, and it's sum of increments, sum of steps plus minus sigma with probability 1/2. So how do we look at it? So this is, for example, what can happen after 8 steps. So there are 2 to the power 8, 32 possibilities, and this is the graph. More likely we return back to 0, a bit less likely here or here, then here and then here, and so on. But, oops, yeah, so let me just do it, put it back. So 16, it gets this, 32, you get that. And what I did in these pictures is I renormalized this graph, so it's more or less the same width. And then what you actually see is that of course, after 32 steps, generally we will go much further away. But if you renormalize it, you also see that it will be this bell shape, which is called Gauss Curve. And it's one of the most, somehow it's, I'm battling my computer. I got a new computer, and then it doesn't play old presentations. For some reasons I don't understand, so, for example, this is already fairly close. And it's something which is ubiquitous in nature, so you see this curve everywhere. For example, if you take all men in the room and take their height, you will see more or less this curve. And the reason is that just how tall you are, it's a combination of several independent things. For example, how much meat you have eaten when you were small, how much sunlight did you get, what is your genetics. And these things are more or less independent, so it's plus minus sigma for each, and then you get the result this. Of course, for example, if you take all men and women, that each of the group will have a bell curve, but that some of them will be curved with 2 bells because there is a significant difference. So it's also occurrence that sometimes you see not one bell curve, but some composition thereof. But this is a very, very important thing in science when you have independent increments. And the question which I posed is how far would you go? So xt is sum of these increments, and well, every mathematical talk should have one proof, so this is one proof. What is the expectation of xt? So expectation, mathematicians, letter E is used for expectation, is the average value. So we should plug in, instead of each s, with probability 1/2 plus sigma, with probability minus 1/2 minus sigma. So the sum expectation will be 1/2 of sigma plus 1/2 of minus sigma, so 0. So expectation of x is 0, and you clearly see this on this picture because it's symmetric. You are as likely to go negative as to go positive, so on average you stay at 0. So the correct thing is then to measure absolute value of x. But absolute value of x, well, it's very difficult to open brackets, so usually people measure square of x. And if you do square of x and the square of sum of increments, and if you sum a plus b plus c squared and you open the brackets, there are 2 types of terms. Terms like a squared and terms like a times b. And here a miracle happens. All terms like a times b, they are 0. Why? Because it's a product of 2 steps. One step is plus minus sigma, another plus minus sigma. And if you take a product and take all the possibility, 2 pluses, 2 minuses give you sigma squared. Plus minus and minus plus give you minus sigma squared. And it cancels out. So the whole thing cancels out except for terms on the diagonal when you square them. And in this case, you get sigma squared. So the answer is sigma squared times the number of steps nt. So conclusion is that on average, square of the number how far you are away is square of the speed, which is quite logical, times the time which has passed. And if you take the square root, you get that the how far you are on average is speed times square root of the time. So at first it's a bit striking that you spend time t walking and you go square root of t away. But there is lots of redundancy. You open the return. So for example, if the sailor walks in the city and he makes 100 steps, he walks on average about 10 away. If he walks 10,000 steps, on average he walks 100 away. So the speed is much less because of this redundancy, and it actually leads to similar phenomena in all physical problems where you have second derivative in equations. So, for example, heat propagates very slowly because of that, because it propagates basically by Brownian motion, by molecules they spread vibrations from one to another by Brownian motion, so heat propagates very slowly, and that's the reason why it takes a long time to heat the room unless you install some ventilator or something. And Albert Einstein noticed that if you do this calculation, you have precise measurement of how far you walked, depending on the speed and the number of steps, but the number of steps is how many molecules bumped into your particle. And that you can count knowing the surface area of the particle and the number of molecules and the speed they walk. And this is the paper he published, so it was 60 years after Brown, so the names of the papers were still longer than today, but not as exciting. So it's on the molecular theory of heat, so here is translated, of small particles that spend in stationary fluid, and the abstract said that you actually get a formula, so this is the formula, where you can calculate all the things. So you relate speed you observe of particle which moves to the number of molecules in a liter, speed of these molecules, which depends on the temperature, the surface area of the particle, so this is why you have pi here, because you assume that it's spherical. And it turns out that all these things you can measure, and you can check whether the theory of molecular matter is contradictory or not. Because you just observe in the microscope your particle, you clock how long it walks and how fast, and then you compare it to the other knowledge. And when he published it, Jean Perrin, who was a famous French scientist, he used it to recalculate the Avogadro numbers, how many molecules there are in 1 mole of substance, and he wrote a letter to Einstein, which was really excited. I never thought that theoretical physics can give such correct predictions that you actually can measure in the lab, and I think he got it like within 5% correct, and so he got this first verification of the existence of atoms. Well, one of two first, the same year there was black body radiation, and also he got Nobel Prize some 20 years later. So the next step was that this was a discrete process. But if you take these small jumps and send them to 0, like in this picture with the bell curve, you can also ask how this curve will look like. And of course, you should probably rescale it. And since after time n, you go square root of n away, it should be a function which you rescale on one side by 10, on another by 100. So it's an interesting thing. It's not homotetical like most things we know. We rescale 10 here, 10 here. Here you rescale in one direction 100, in another 10. And this function, the limit of it, was rigorously constructed by Norbert Wiener, who is famous again, not for this, but mostly for computers. It was an interesting random function, so it's called Wiener process or sometimes Brownian motion. And the interesting thing, he didn't construct it as a random process. It was later constructed by other scientists as a random process. He constructed it as a random sum of sine functions. And the coefficients, you should put random coefficients, they are not plus minus 1s, they are exactly these bell-shaped curves. This n stands for normal distribution. Now, why sine function? It's a very interesting story. It has to do with Fourier transforms. It has to do with them being eigenvalue, important functions for the second derivative. So second derivative of sine is minus sine, and this is what comes into play. And Brownian motion is related to sine. So this is a thing which had numerous applications in science since, and even before, and it's everything from physics, where I mentioned biology and physics, but for example, important one is economics. So there is a thesis which was actually written by Louis Bachelet. For some reason, there is only one surviving picture of Louis Bachelet when he was a high school student. It's the year when he applied, I think, to go to high school, which prepares for École Normale in France. And his theory was that the price of stocks is actually given by combined effect of many people randomly buying and selling them. And so you get a Brownian motion. Of course, it has some, as they say, drifts. So for example, if there is a war in the Gulf, then the oil gets more expensive. But if you take out this extra things, which usually are easy to account for because you just read newspapers and see what should happen. But then you get Brownian motion. And it turned out that it gives you much better ways to predict this, what will happen in the long run on average. It took till 60s to realize that. So for 40 years, people were predicting the price of European stock options by just comparing what they have now with the tables of historical data. And then Black and Scholz, they came up with a formula which used Brownian motion, which was very easy. And then Scholz, Black was dead by then. With Merton, they got the Nobel Prize. And it's a formula which is still used today. But one of them founded a company and then chose and got bankrupt because this formula works very well as long as there are no blow-ups, no crises, and when there are crises, you get discontinuous function, and the formula no longer works. So it's very useful as long as the market is stable. But this is all historical thing, and I wanted to say a few words about modern theory of random walks. And this is a very recent theorem which made quite a splash less than 20 years ago. And this is a theorem about two-dimensional random walk. And Benoit Mandelbrot asked a question, what can you say about the curve of Brownian motion? And he plotted this curve, and the curve goes many, many times over the same place, so you don't see much. And he said, well, I want to see a curve, so he erased everything inside. So he left only the boundary of this. Like, you can think that this is an archipelago or an island, and you look just at the shore. And he conjectured that it's a fractal curve of a dimension 4/3. And that was proved by Greg Lawler, Adet Schramm, and Werner in 2000. Before it was sort of explained by theoretical physicists. And I must say a few words, what does it mean a fractal, and what does it mean a fractal curve of dimension 4/3? A fractal, there is no mathematical definition of fractal. So what Benoit Mandelbrot suggested, that fractal is a self-similar figure which is not smooth. So for example, his first paper, he used the coast of Norway as an example. So it's not smooth. And then how do you study it? So for example, you want to measure the length of the coast of Norway or the length of this random curve we had on the previous slide. So what do you do if you measure the length of an interval? You cover it by grid L by L, and you count how many squares you need. And then you count for small squares and so on. So for example, if you want to measure the coast of Norway length, you cover it by squares of 500 by 500 kilometers. Count how many you need, multiply by 500 kilometers. Then you cover with squares 100 by 100 kilometers, count how many you need, multiply by 100 kilometers, so on and so on. And you should get length. And if you have a smooth curve, you would get length fairly fast. But if you have a really fractal curve, what happens that once you start using squares of size 100 kilometers, you start entering into the fjords. So you get a bigger length. 50 kilometers, you enter in a subfjords. Like 5 kilometers, you enter into small bays. 5 meters, you analyze individual rocks, so it gets longer. And the definition of a fractal dimension is that it's the power of L you need to take to account for this. And what what Mandelbrot predicted and Lawler, Werner, and Schramm have shown that if you cover by grid L by L Brownian motion, you need L to the power 4/3 small cubes. So it's very, very, very wiggly. And this is like a common quote of Benoit Mandelbrot, that clouds are not spheres, mountains are not cones, and the lightning doesn't travel in straight line. And what he wanted to say that indeed in nature you often see non-smooth shapes, fractal shapes. So this is the, type of cauliflower, Romanesco, which is very regular, very self-similar, very fractal. This part of Mandelbrot set, which is archetypical object in the ecosystem. This is a glacier from the air. This is lightning. And above there is a sort of common mathematical example. Let me run it again. So it's called von Koch snowflakes, so Helge von Koch. He was at Cotejo, not at Cotejo 120 years ago. And this is, it's kind of computer, yeah, okay. So what you do, you take a triangle, and then on each side you put another triangle, on each side you put triangle. So he actually did it to give an example of a function without derivative. But it also gives an example of a fractal where it's fairly easy to calculate dimension. It's logarithm of 4 over logarithm of 3, so approximately 1.26. And now, I've said about something 20 years ago, so here's something more recent, which is now in progress. So it turned out not only that the boundary of Brownian curve has dimension 4/3, that there are two other curves which come from important problems in physics and chemistry, which also have the same dimension. So this is what is called percolation cluster, so it's also like an island, but a different one. This is what you see if you have a forest fire and you make a picture from above. And the burned area will look like that. So it won't have straight boundaries. Well, of course, okay, so if you have like forest fire now in Los Angeles, of course there will be sometimes straight boundary when it burns up to the highway or up to the shore. But if it stops in the middle of the bushes, it will always be fractal. Turns out the boundary is the same fractal with dimension 4/3. And here it's a picture of a model which is called random polymer. So it's, I'll say a few words later, but it's basically, you should think of it as a polymer molecule randomly thrown into space, how it will look like. So these two are known to be the same in 4/3, and this is like half known. So we have half of the theorem, well, if you can say so. So we know that it is so, we can explain why, and there is one small lemma missing. So if you want to do mathematics, I think it will be there, this lemma missing in 5 years still, unless you do it. What is percolation? So this is a model for many things, spread of epidemia or gossips or erosion. So this is, for example, erosion. You start chipping random grains of sand and you end up with something fractal like here. And the easiest way for it is not a dynamical model, but it's a model for a rock, porous rock. So you toss a coin for every hexagon, and heads or tail. If it's tail, it's yellow, it's a piece of rock. If it heads, it's white. If it's tail, it's white, and then it's a hole. And then you put water on top, and can you seep through? So if you put water here, no, you cannot. You put here, you go, no, it's dead end, but you can go around. So here you can, no, you cannot. Yes, you can seep through. So here, yes. So this is, I put blue on top, so it seeped through. Now, in real life, the scale of molecules of holes is much smaller than the scale you observe. So you should take smaller, pass to a limit. So can you see whether one can seep through here or not? There are pictures where you can, there are pictures where you cannot. It's a probability theory. Well, we can have a democratic vote. I actually see the answer. So if you cannot see it, you should consult your oculist, your eye doctor, and I can suggest a telephone where I take small commission to have new eyeglasses. So here, you actually cannot. But the reason why it's difficult to see, so the main question is why it's difficult to see, is that if there are crossings, they are fractals of dimension 4/3. And this is a theorem. And now, if a square is, for example, 1,000 by 1,000, how much is 1,000 to the power 4/3? So how much 1,000 to the power 1/3, cube root of 1,000? Cube root of 1,000 is 10. So 1,000 to the power 4/3 is 10,000. So if there is a crossing of a square 1,000 by 1,000, it's 10 times longer than the side. So it's very wiggly, so it's very hard to see. And ironically, you see this in forest fires. So I don't suggest you to experiment, but there are enough pictures on the web. If you really analyze the pictures, you will see that there is a fractal boundary. And if it's million by million, million to the power 4/3 is not 10 million, it's 100 million. So there it's even wigglier. So it's really this sort of a fractal. And the interesting thing that this problem was first posed by material scientists and by physicists, so they were studying filters for the gas masks. But then someone discovered that in the very first volume of American magazine for high school kids in 1894, this problem was posed. And actually, look which problems they were solving in 1894 in high schools in the United States of America. In 1894, yeah. Actually, it's a very good question why this problem was possible in 1894 and not, say, nowadays. So who has a guess? Why would you never see such things in modern journals? No. It's a young French guy, Henri Lebec, in defending his PhD thesis in 1904, 10 years after that, and he discovered that there is a better way to integrate than from A to B. So before people, if they wanted to integrate over three-dimensional space, they had to integrate with respect to one coordinate, second coordinate, third. He discovered that you can just integrate with respect to the area. So you no longer write this, you just write integral with respect to the area. And he discovered also there is a better way if you have a function. The best way is to integrate not left-right, but up-down, taking vertical, horizontal cross-sections. And it really changed this area a lot. But so that you don't see now in the books. But this problem it's quite interesting because they ask that you put randomly both in the box, and then you ask whether you can pass from one side to another, and then they immediately publish a solution, and the solution says, well, of course, if you can pass, the crossing will be straight, which we see is not the case. And then they calculate probability for a straight crossing, which is very easy textbook exercise, and they get it wrong. That's really hilarious. And then there is editor's note. This solution is not entirely satisfactory. So if you get correct one, we will publish it. So it's funny, no one knew it. It's one of my friends found it 6 years ago that apparently this question was asked out of pure curiosity. And in the remaining, yeah, I have like 5 minutes. Yeah, that's, no? Yes. Yeah, okay, well, okay, yeah, it's you know, Swiss training, you said 1845, I said 18. Well, yeah, so it's, yeah, in Switzerland you are supposed to finish on time and put the dot in the last square of the blackboard with it completely filled by formulas. So it's sorry? Yeah, that's blackboards, yeah, okay, the last slide. So what is a random polymer? So it's a question which arose in chemistry, and the question is that if you have a long molecule, how it will be positioned in space. So it's sort of, even to a lay person, like mathematician like me, it's clear that it's a question which should influence its chemical properties, which things are more pronounced or not. And if you, for example, take a DNA molecule, so how long is the DNA molecule? So it's a question to high school kids, approximately. This long, 1 kilometer. Your DNA or my DNA. Yeah, it's about, I think it's a bit less than 2, I don't remember, but, well, there must be biologists, but it's that order of magnitude. Also, it's a question, I mean, what does it mean to put it straight, because, yeah, but it's more or less if you put it straight about that long, so it's clear that in our cells it's really compressed, and it's sort of a picture like that, and at some points some pieces of it are straightened for replication. And the question which is related to this model is what happens if you take this molecule and put it in some solution that it unwinds. And it unwinds not in a straight line, but rather in a fractal curve. And the question was asked by Paul Flory, who is a famous polymer chemist who got Nobel Prize also, but for a different thing. So he suggests a very easy model, which is called self-avoiding random walk, or self-avoiding walk is a better word. So you take all curves of length n, all walks of length n on a lattice, but you're not allowed to visit the same place twice. I immediately point out that it's much more difficult model, because if you walk and you're allowed to go as you wish, you don't need to remember your past. So you only need to remember where you are. So even a drunken sailor can perform it. Now suppose that you go wandering in a big city and you don't know, and you're not allowed to visit any place twice. You have to remember the whole trajectory of yours. And it can happen that you go happy, lucky, and suddenly you come to a place where you turn into a square and there are 3 streets coming out of it, you visit all 3 of them. So you are stopped. So there are some trajectories which you cannot continue. There are some trajectories which are easy to continue. So it's much more difficult. So he did a conjecture that while the normal random walk in n steps goes square root of n away, this goes n to the power 3/4 away, which is sort of logical, because if you're not allowed to return to the same place, you should go further away. So power is bigger, 3/4 is bigger than 1/2. And it sort of translates that in n steps you go n to the 3/4 away. So if you have a box of size r, then you made r to the power 4/3 steps inside, so dimension is 4/3. So he had actually an interesting argument, which it's so-called Landau mean field theory, which gave this number, and then another French chemist, also a famous one, Dejean, has shown that the argument is wrong, and people forgot about it, but it turns out the argument is wrong. In one place you lose something, in another place you gain something, and you lose exactly as much as you gain later. So it's actually, the answer is correct. And we cannot prove it, but what we were able to prove, it's fairly easy to see that if you count how many curves there are, then it grows as some number to the power n, and number depends on the grid. So we've shown that for hexagonal grid, this number is square root of 2 plus square root of 2. And I assure that there is no like trivial way to get this number. So this actually, it's twice cosine of pi over 8. Yeah. So it's, and this was conjectured before by physicist Nienhaus. But also he conjectured a bit stronger behavior. He conjectured the behavior is mu to the power n, where mu depends on the lattice, times n to the power 11 over 32. And 11 over 32, if for thirds you can imagine getting in an easy way, this is much, much more difficult to get. And it's, how can it be that the main term depends on the lattice and the next term is universal? Well, because it's statistical physics, it's like, for example, boiling a liquid. Different liquids boil with different temperatures, like spirit and water and oil, they boil with different temperatures. But they boil exactly in the same way. So mu plays the role of the temperature, and 11 over 32 plays the role of the characteristics of how the process of boiling goes. So the way we prove it, we define some function on the lattice, and we observe that this function satisfies what is called in school first Kirchhoff's law. So it's the law that if you have if you put on the grid electric current, then for every point the amount of current which emanates and which comes into it is 0. And this is sort of conservation law. If you have this property at every node, then you can deduce some global things like the amount of current which leaves the box is equal to amount which enters. And this allows to do some estimates of this curve. And the interesting thing is that in our proof, if you get the second law, which is the current around phase is 0, if you get it asymptotically, we'll also understand how you get these two other numbers. But so far, we did this, well, it's actually 2012, but it's still kind of a way, but we too haven't thought about it in a while. So I think this is just an example how random walks still continue to be exciting, and I think I'll thank you for your attention, and there are I have 5 more minutes just in this case that I started late. And this is a question, are those pictures similar or not? Well, the one on the right is not exactly hexagonal lattice, but it's almost hexagonal. So the question is, does the right picture look like percolation? And what is on the right picture also? That's the question. So the answer is actually, it's sort of like percolation, but it's actually turned out to be what is called Ising model. It's a bit more complicated, and the picture on the right is actually a picture of a back of a lizard, of a real-life lizard. It's bites like hell. It's not to scale here. It's like that. It's not that big. But my friend biologist, Belgian biologist who works also in Geneva, so he brought this lizard and asked, does it look like percolation? I said, well, it kind of looks like, but it's really what struck me that most squamates, well, I mean, that means lizards or snakes, they have a kind of pattern which disrespects the scales and which have round things and so on. You see sort of trace here, but it's not that. And I said that I never seen anything like that. He said, well, there are some species. And what happens is that when the lizard is young, it's covered like the usual reptile, so it's, there are actually 3 different covers, and it goes across the scales. And then when it grows, so it's to scale. So the small one compared to the grown one is like that. But when it grows, the covers start changing, and eventually at about 1 year, they all flip, or even before, about half a year, they all flip into green or black. And then occasionally they flip from one to another. So you get these random coverings. The reason why is sort of clear, because this cover is good for hiding, but if you stretch it, it's no longer good for hiding in the same places, so you need to change covering scheme to be able to hide well. But the question is how you get this picture. And here another great guy comes in. So Alan Turing proposed in 1952 in one of the last papers of his a mechanism how animals get patterns. And at the time, no one believed him. And then chemists observed this phenomenon about 30 years ago, and biologists only observed it, really proved that it's the case for a few species, for some fishes, 15 years ago. So the idea is that you have diffusion equations which are exactly the Brownian motion. So you diffuse very slowly, so you have a pigment, you have a black spot, it diffuses, you become gray eventually. But suppose you have two different pigments, and there is a chemical reaction between them. That the first one is catalyst for the second, and the second one is inhibitor for the first. So what happens? The first one exists, it's catalyst for the second, so you create a lot of the second one. But the second one kills the first. So there is little first, but there is little first, so there is little second. But if there is little second, it no longer kills the first, first appears, and forces creation of the second. So you can have a vicious loop, and the interesting thing is that basically everything can be explained by this. It's very easy equation, so this is a discrete version. So for example, this zebrafish for whom it's basically proved that it's the case. So people were doing experiments, they were running computer model, and they were also burning with laser a part of the color of the skin of the fish and changing to zero values in a part of the matrix in computer. And then it evolves exactly in the same way. This is a computer experiment done by Turing by hand. So he had no access to computers anymore in 1951, so he decided to test his hypothesis, and he did 10,000 iterations by hand on a piece of paper. So I'm telling to modern graduate students, and they say, well, yeah, people had more free time back then. But, yeah. This is an example, if it will work, of movies where you have different values for, oh gosh, it doesn't work. Yeah, so it's... So this is you take the same functions with slightly different values, you have completely different behavior. So you can see that, for example, leopard skin can be generated by this. Like this is not, well, this is not yet tiger, but it will be tiger in like half a minute. So it's by changing a little bit the parameters, you can generate it. Of course, the question is how nature does it. Well, nature tries all the possible, nature sees which coloring is more efficient, and then tries all the possible ways to get it, and then the cheapest one is retained. And this one is the cheapest because you just say which pigments you have and what concentration to start with, and then it assembles itself. Now, what happens with the lizards? Why it's not across the scales? Because if you cross-cut through the scales, the interspace thickness is much less. So there is less diffusion. And you actually can argue, and we even have a theorem, as much as you can have a theorem in biology paper, that you can assume that every scale is of the same color at almost any time. So actually you run this not on a plane, but on a lattice of scales. So each scale has fixed concentration. So we reduce it to discrete model. And discrete model we reduce to something which is called cellular automaton. And miraculously, I mean, first we almost have a proof, and second, if you do run computer experiments, so here there was, the first one was a real life, and the second one is the computer simulation, you get exactly the same picture. And what was even more exciting that we took the numbers which are for zebrafish, because they are the same pigments, and then we have a formula how you reduce the numbers for continuous to the numbers for the lattice, and it immediately fit every picture we have seen with very good precision. So I've never got so much respect from biologists as a mathematician, because they said, well, yeah, you actually can do something reasonable. And they said, but first we didn't understand why you had to divide by square root of 3 in your formulas. I said, well, because it's hexagonal lattice 60 degrees, cosine of 60 degrees is square root of 3. I said, well, but now you get our respect for square root of 3 has the place. And it's really was as precise that on the tail they have bigger hexagons, and they're usually half and half, and in our model it's the same. If you double the size of hexagons, you get different patterns. So you see, it's even keeps popping up in other subjects, and well, thank you for your attention. And this is the lizard to scale. It's that big.
Thank you very much, Stas. Talking about Brownian motion, you said that I forgot to tell the audience that you also are a foreign member of our academy,
like Brown. Yeah.
Like Brown, a great club to be joining. This looks like the game of life. This is about
so the interesting thing is that it looks like game of life. I actually had slides with game of life, but I deleted them not to have too many slides. So actually, it looks like, for those who know statistical physics, it's actually Glauber dynamics for antiferromagnetic Ising model, which is frustrated. But, well, like there are at least 4 persons in the audience who know it well. Well, and so it's kind of a random game of life. So you look at a hexagon, you count how many neighbors it has, for example, 2 green and 4 black, and then depending on that, you toss a different coin to decide to flip it or not. So theoretically, there are papers, and I can even do it better way, to show that you can come up with a reaction diffusion equation with very obscure coefficients, which will lead exactly to game of life. But that would be rather sensitive to perturbation in coefficients, whereas this is very robust, so it's unlikely you will ever see such a lizard. But the nice thing about this particular one that it is, we actually don't know, because there is a whole range coefficient which works. We don't know if lizards live forever, whether they will keep flipping colors all their life. Because in part of the range, what happens is that eventually they become totally black. But on a in midterm, you have the same picture. In another part, they keep flipping forever. And I don't see any reasonable way to check it. And keep flipping forever, it's interesting because it's related, I said, the antiferromagnetic Ising model. That's not in that paper, it will be in the next one, because we didn't have enough data. So antiferromagnetic Ising model, it's a model where all hexagons neighbors try to be of opposite color. If you run it on a chessboard, there is an easy way to do it, chessboard coloring. But if you run it on hexagonal lattice, at every point 3 hexagons meet. And you can't have them each 2 of opposite colors, because if you start yellow, this one has to be white, this has to be yellow, and, well, you get a contradiction. So when you try to do chessboard coloring on hexagonal lattice, you always run into many, many problems. So what physicists say that it's frustrated, so it creates some complex structure. So it never rests, you keep flipping and flipping and flipping, and you get nice patterns like this one.
Well, they get black and we get white when we get old, yes. Any questions? Yes?
Yeah, Mikkel.
There's a mic coming in. Incoming.
You mentioned Nino's formula, but he used sort of Coulomb gas techniques to make this prediction, right?
Yeah.
So
when we sent him our paper, he said, "Oh, it's so good, now I understand my own proof." Yeah, that was very well. He has sense of humor, yeah, he's a very nice guy. And yeah, he has Coulomb technique, gas techniques, yeah. So here, what Nienhaus did, so he's a physicist, so he gets paid not for proving theorems, but for explaining why they should be true. So he considered configurations of not only this curve, but configuration curve plus many, many loops. And then, if you have collection of loops, it looks like a geographical map. Like geographical map, every loop is like well, in mathematics you call it Lebesgue curve. It's so how you draw a hill? You draw one loop, another loop, it's the curves of height 100 meters, 200 meters, 300 meters, and so on. Only you have to distinguish the curves by orientation, whether you will draw a hill or you draw a hole. So what he did, he took collections of loops, put random directions on them, and that gives you a function. And then the functions which you get from different models, for example, for this model, for percolation, or for Ising, or all these 3 models, you get the functions which have some nice physical properties. We cannot prove it, but it's almost clear it should be true. And if you assume these physical properties, it turns out that when you pass to a limit, instead of Wiener-Brownian motion, you will have its generalization to a plane, you will have like random landscape in the plane. And mathematicians call it Gaussian free field, and physicists call it a free boson. And this is a function which is very well studied. You can calculate all the things, and then you can come back and you get funny numbers like 11 over 32. Well, nice number, I don't know. Is it a funny number? Yeah, I think it's funny, yeah. Yeah, so, but he does this. We still cannot do it. We still cannot do it. We can formalize it step by step, but there would be 2 or 3 lemmas which are missing. And one thing, if you ask a specialist question, I don't know how to formulate this method in a domain. I only know how to formulate it on a torus or on a cylinder, not in a domain. There are boundary conditions I don't know how to do. No, well, I mean, we don't know. No one knows. Yeah.
Okay, maybe I have another question.
was amazed that Turing worked in this area. I mean, it's really. Did you write more about biological problems?
Well, with Michel Milinkovic, we have two more, well, maybe more projects. I mean, we will have a. It turns out that it's really the numbers are very closely related to the Ising model, so it will be another paper. But also the interesting thing is that the way it gets scales, it's also by reaction diffusion equation. So there are different substances which, well, when lizard is born, it's a perfect sphere mathematically. Well, not perfect sphere, but okay. And then it's basically a question at one point why it's not a spherical one, why it's something protrudes. And the reason is that, of course, there are small perturbations which start, but if you just have a small perturbation, you would have a curved sphere. But what happens that there are substances, other substances not having to do with color, for which you solve reaction diffusion. And at one point, the solution becomes a hexagonal lattice. So there is big concentration in hexagon, small concentration on the boundary. And then at one point, a comment kicks in that when you have big concentration, these things consolidate to form a scale, and the small concentration, they become interscalar space. So it also becomes, they have almost perfect hexagonal lattice, and it's also done by solving another reaction diffusion equation. But you see, I mean, it's very economical for nature. It's very, if you write a program, computer program or genetic program, it's very easy to define reaction diffusion equation and give coefficients. What computationally, then it's not easy to solve it. But nature doesn't care about that. It's the lizard who has to solve this equation to get the scales. And then she or he gets the scales, solves and gets the scales. But that is an interesting thing. Yeah, it's actually we're discussing. You know, I'm using things. It's like Michel came that like, look, I mean, topologically lizard is a sphere, and topologically you cannot. Topologically lizard is a sphere, but you cannot cover sphere by hexagons. You should have at least you should have exactly 12 pentagons by Euler's formula.
Like football.
Well, they actually have pentagons in some places. Yeah, so it's yeah, but that one can study. Yeah.
So that's a new area in biology to study, is to model, for example, development of fetus and things like that. And
oh yeah, it's a big thing, but it's really amazing. I mean, it was 100 years last year of this first mass biology book on growth and form, and which was mostly about shells and things like that. Darcy Thompson, and but the interesting thing that now, for example, this like morphology, all this, it's for example like how we get fractal structure of our brain. I think there is a Harvard guy, Krishnan, who has a paper. Basically, the idea is that you take two substances which with different stretching properties, and you start inflating them, and the top one stretches faster than the bottom one. And then automatically it sort of collapses into fractal space like our brain surface. And I mean, he runs it in a lab, and then you get thing which looks in space in shape very much like our brain. So there are cheap methods of getting, but it is even simpler than reaction diffusion, of getting complicated shapes.
Any more questions here? No? What you said about Turing, do it by hand, I remember there was a book called When Computers Were Human. It was a job to be a computer, actually. Now it's machines.
No, but I mean, it's something that's actually impressive. Like people were doing computer experiments by hand. It requires, some focus, yeah. I don't remember the actual number of research, but it was in the thousands. So it's basically... yeah, it's not well. It's in very easy formula because you just each time you add average of your neighbors plus this function, which was the interaction was very easy. So it was easy to do, but we instead for our lizards we run computers overnight and make pictures of lizards 5 years in a row in the lab. Yeah, so it's.
So, I mean, you've spoken quite a bit of reaction diffusion equations, and of course there are more. And do you sort of, this is a philosophical question, should these can have been used in biology. Do you think that they should be emphasized in math biology? There are other questions, like neurons. There are these. There are various.
Well, I never thought about it, but you know, off the top of my head, I mean, biology is such science that you shouldn't have any other equations by diffusion. Well, I mean, mostly 90% of cases, because you know the things like other phenomenology, like there are like wave equation, for example, which has completely nice other phenomenology. You have it in physics, but in biology you normally would not have it because of the structure of the tissue. So most things will propagate with will propagate with square root of t speed. So it's mostly will be diffusion, and overall in nature most equations are second order. There are a few exceptions. So it's.
I was thinking of a paper by Piesen and Yushchenko, sort of, they discuss about 6 models of reaction diffusion equations, which with some biological applications, or so for me.
Oh, there are infinite books about reaction diffusion equation. It's the sad thing is that you cannot easily classify their behavior. So if you do it in one dimension where they were first introduced before Turing by Kolmogorov and I want to say Pitayevsky, I think, yeah. But in one dimension you don't get, I mean, what kind of pattern you can have in one dimension? You can have only like a periodic pattern, white, yellow. So they did not observe this nice behavior. Now there is like informal classification what kind of patterns you can have in dimensions higher. So you can have stripes, you can have dots, you can have labyrinths, and basically, but there is not like really mathematical theorem behind it. On the lattice, we sort of, in what we are writing, we'll probably have some sort of mathematical theorem which explains what is going on, relating it to some strange attractors for a normalization flow of the Ising model. But it's very difficult to classify, and especially if you, well, I mean, of course, there are, in 2 dimensions, there are some topological considerations, but so you won't have, if you have a stripe and you have another stripe, they don't cross, or if they cross, it's just one figure. But I don't think there is like a satisfactory theory which is mathematical. But as far as applied math is concerned, there are many books and what is known about their behavior. Yeah, so it's. But Turing's paper really, it's kind of visionary. It's like ancient Greeks suggesting out of philosophical reasons that you would have molecular structure of matter. So at the time, I think no one believed him that it's the reason for different shapes. I think at the time people were probably thought that in the genome of a zebra it's encoded how you cover it, white, black, instead of that it's encoded that you start running some process. So to say, yeah. And this is basically, by the way, these are, well, it's the same equation, but here, because of the boundary data, you get stripes. So it's.
Any more questions? Oh. Also, let's thank the speaker again. Thank you very much. Very nice talk.